Oakley Dokley, chapter 29, number 22. A circular loop of wire with radius r equals 0.0480 meters, that's a lot of digits, and resistance r equals 0.160 ohms, is in a region of spatially uniform magnetic field as shown. The magnetic field is directed out of the plane as indicated by my little dots, aka bullets. The magnetic field has an initial value of 8 Tesla and is decreasing at a rate of dB dt equals negative 0.680 Teslas per second. Is the induced current in the loop clockwise or counterclockwise? Okay, so the way I like to do this is with pictures. So initially, we've got a loop, we've got a bunch of magnetic fields coming out of the page. My magnetic field is decreasing, so now I have less things coming out of the page. Induced EMF is created in such a way to keep things the same. So if I start with 1, 2, 3, 4, 5, 6, 7, 8, 9 dots coming out of my circle, I want to keep 9 dots coming out of my circle. So my induced EMF is going to put 4 extra dots. So if I start with 9 dots, my field decreases to 5 dots. My induced EMF is going to pop in 4 more dots in order to keep us how we started. So pictorially, a decreasing field is decreasing my flux. So my induced EMF is going to oppose that decrease in flux by giving me a field in the same direction. So from my right hand rule, my induced field is out of the page, so my current is going to be going this way. Okay, so we can also think about it the equation way. Minus d flux dt. My flux is currently out of the page. My field is decreasing, so my change in flux is into the page. Negative change in flux is out of the page. So my induced field is out of the page. My induced current is that way. So you can look at it either way. You can either look at it from the equation or from drawing pictures. Personally, I like pictures because they're more intuitive, but that's just me. All right, so part B, what is the rate at which electrical energy is being dissipated by the resistance of the loop? So our induced EMF is minus d flux dt. So our flux for a time, so our flux is B times A. So B times pi r squared. The time derivative of my flux, d flux dt. Pi and r are staying the same size, but my B is changing. So dB dt. So dB dt times A is my change in flux. So my EMF is the minus change in flux minus pi r squared dB dt. So this would be minus pi. My r is 0.0480 meters squared. My dB dt was given, it's negative 0.680 Teslas per second. So the EMF induced is, where's the pi? There it is. All right, pi times 0.048 squared times 0.68. So my induced EMF is 4.92 millivolts. Okay, so that's just the induced EMF. That's our voltage that we get. So the rate at which electrical energy is being dissipated by the resistor, electrical energy being dissipated is a fancy way of saying how much power is dissipated. So for a resistor, P equals IV. Or from V equals IR, it could be I squared R. Or it could be V squared over R. So we know V, we just found it. We know R, we were given. So let's use that one. So it's going to be my 4.92 milli, so 10 to the minus 3, volts squared over R was 0.160 ohms. The power dissipated in my resistor is 1.51 times 10 to the minus 4 watts. Huzzah!